Welcome to the video lecture for section 6.4. This is for MIC 1105, College Algebra. My name is Jorge Young. So in 6.4, we're going to go ahead and change exponential statements to log statements and then log statements to exponential statements. We're going to evaluate log expressions. We're going to determine the domain of a log function. We're also going to quickly look at graphing log functions and then solve log functions. So the formal definition: a log function with base a, where a is greater than 0 and a does not equal 1, is denoted by y is equal to log base a of x, and is defined by y is equal to log base a of x if and only if x is equal to a to the y power. The domain of the log function y is equal to log base a of x is greater than 0. So now we're going to change exponential statements to log statements and log statements to exponential statements. So changing the exponential statements to log statements, we're going to change each of these. Each of these is an exponential statement. We're going to change it to an equivalent statement involving a log. So for the first one, if 1.2 to the third power is equal to m, then 3 is equal to log base 1.2 of m. Remember, y is equal to log base a of x is equal to x is equal to a to the y power, and where a is greater than 0 and a does not equal 1. Now, if e to the b power is equal to 9, then b is equal to log base e of 9. If a to the fourth power is equal to 24, then 4 is equal to log base a of 24. I'm going to change log statements to exponential statements. So the first one, if log base a of 4 is equal to 5, then a to the fifth power is equal to 4. If log base e of b is equal to negative 3, then e raised to the negative 3 is equal to b. If log base 3 of 5 is equal to c, then 3 to the c power is equal to 5. We're going to evaluate log expressions. So we're going to find the exact value of each of these. So for a, to evaluate log base 2 of 16, think 2 raised to what power yields 16. Then 2 to the y power is equal to 16. We're going to change it to exponential form. We're going to get the same base. So 2 to the y power is equal to 2 to the fourth power. And so y is equal to 4. Now for b, we have log base 3 of 1 over 27. So we're thinking of 3 raised to what power is going to give me 1 over 27. Then 3 to the y power is equal to 1 over 27. 3 to the y is equal to 3 raised to the negative third power, so y is equal to negative 3. Then determine the domain of a log function. So domain of a log function, the range is equal to the range of the exponential function, and the range of a log function is equal to the domain of an exponential function. So y is equal to log base a of x. We can define the equation x is equal to a to the y power. So the domain x is between 0 and infinity, which means that x is greater than 0, and then the range is all real numbers for y. So find the domain of each log function. So we have a, b, and c. So the domain of x, and f is log base 2 of x plus 3. And so what we do for all x plus 3 is greater than 0. That means x is greater than negative 3. So then using interval notation, the domain of f is negative 3 to infinity. For b, we have log base 5, or 1 plus 5 over 1 minus x. So the domain of g is restricted to values that are greater than 0. So we're going to solve this inequality to find the domain of g that consists of all x between negative 1 and 1. And so therefore x is between negative 1 and 1 using interval notation is negative 1, 1. Now, for c, log base 1 half is equal to the absolute value of x. Since the absolute value of x is greater than 0, provided that x does not equal 0, the domain of h consists of all real numbers except 0, and that's the interval notation. Now, y is equal to the natural log of x if and only if x is equal to e raised to the y power. So here's x, here's natural log of x. You can see that they're symmetric about the y is equal to x line, which means that they're inverse functions. So here's y is equal to e to the x, and here's y is equal to the natural log of x. So y is equal to log of x if and only if x is equal to 10 raised to the y power. If it has no value here, no base given, it's 10. And so here's y is equal to 10 to the x power, and then here's y is equal to log of x. So we're going to go ahead and solve log equations. So we have a and b. So for a, what we're going to do is we're going to change the log function to exponential function. And so the nice thing about this is that what they did here, this is my base, and then I can use 3 as the base for both sides. Once I do that, and on the right side I get 3 to the second power. If I put 3 here as the base, my log base 3 goes away. They cancel each other out, so I'm left with 4x minus 7 is equal to 3 to the second power. That's how we got rid of the log base 3. And then here we just solve a simple linear equation, and we get x is equal to 4. We always check it, and it does work. For b, we got log base x of 64 is equal to 2. So x squared is equal to 64. So x is equal to plus or minus 8, which is a square root method. Because the base of a log must be positive, we get rid of the negative 8, and then we check the potential solution, 8, and it does work. So when you use logs to solve an exponential function, so we have e raised to the 2x is equal to 5. So if I use natural log, as my base on both sides, natural log and e are going to cancel each other out. So here we have natural log of 5 is equal to 2x. And then I divide both sides by 2, so x is equal to natural log of 5 over 2. This is a perfectly good solution. This is the exact solution. We can use an approximation using a calculator. So the solution set is natural log of 5 divided by 2. Be careful with this. This is not natural log of 5 over 2. And that's the end of 6.4. Thank you.